Hello everyone. Our topic is GaussianFormer seen as Gaussian for region-based 3D semantic occupancy prediction. Or seen GaussianFormer, it does image arrangement may be based on Gaussian distribution and map it to voxel. And what is voxel? For example, in the three-dimensional space in the image, the gray square represents a three-dimensional pixel. Pixel can build a three-dimensional model through different position stacking and pixel coloring. What is the use of this? Region-centric systems have economic advantage in the field of autonomous driving, but they cannot capture arbitrary shaped obstacles. Simply put, the system cannot recognize things that it hasn't seen. This problem is solved by 3D occupancy prediction. However, the memory space required by the current solution is too large, such as BEV, TPV, and compression distortion may occur. In this case, objects composed of Gaussian distribution theory can effectively optimize this problem. Comparison of the proposed 3D Gaussian representation with existing grid-based scenes representation. The voxel representation assigns each voxel in the 3D space with a feature and is redundant due to the sparsity nature of the 3D space. BEV and TPE employ 2D planes to describe 3D space but can only alleviate the redundancy issue. Differently, the proposed object-centric 3D Gaussian representation can adapt to the flexible region of interest yet can still describe the fine-grained structure of the 3D scenes due to the strong approximating ability of mixing Gaussian. Next, we introduce the GaussianFormer model, which learns meaningful 3D Gaussian distribution from multi-view images. The entry process is illustrated as shown. First, the 3D Gaussian properties and their corresponding high-dimensional queries are initialized as learnable vectors. Each Gaussian is treated as a point located at its mean, and the generated point count is voxelized.
Let me introduce the image coarse attention modules. This module flat interacts between 3D Gaussian distribution and image features, extracting relevant visual information. It generates 3D reference points based on Gaussian offset and means, reflecting their distribution shape using covariance. These points are projected onto image feature maps using camera parameter. Through projection and attention mechanism, the extracted features are integrated back into the Gaussian for enhanced 3D semantic tasks. And the reference modules. The reference module interactive after the Gaussian distribution address this position and the shape to better represent semantic or spatial features. Using 3D information from previous modules, it refined the Gaussian for greater accuracy. After melting blocks, the refined Gaussian are converted into precise 3D occupancy representations. And the image issues show how spare Gaussian data is mapping on a 2D grid, where each Gaussian has a center, range, and weight. Sorting ensures proper handling of Gaussians contribution to the same grade cells with overlaps indicate shared contributions. In 3D, this expands to a volume where Gaussian are represented as Ellis mass to Vassal, based on the range and the center. Combine these contributions create a distinct 3D occupancy for since reconstruction. And how does the Gaussian distribution change its shapes? If cone xy less than 0, it causes negative slope change, and if cone xy larger than 0, it results in a positive slope change. The shape of the distributions. The convergence matrix defines the shape and the direction of a Gaussian distribution. If the convergence is 0, each dimension is independent and the shape in its circle or 3D. If the convergence is not 0, it indicates a relationship between dimensions stretching the shape into a ellipse or ellipsoid. How it affects the ellipsoid? The eigenvalue determines the length of each axis. The eigenvector indicates the direction of each axis. In summary, the convergence matrix determines the shape and origin of the ellipse of ellipsoid. In the module step, geometry and semantics are handled as follows. In geometry, GaussianFormer using simple concentric results in multi-peak distribution but lacking precision. Purpose method introduce problem execution to filter irrelevant data, improve geometry accuracy. Semantic GaussianFormer overlap semantic distribution make it hard to distinguish objects. In purpose method, create a clear non-overlap distribution enabling better object differentiation. Over the purpose method provides greater precision in both geometry and semantics. And this picture shows 3D semantic segmentation results from multi-view images. Pink represents drivable surface, green is vegetation, yellow indicates car, and the other color represent offset, pedestrians, and more. This highlight how multi-view images are combined to create accurate 3D segmentation with different color currently representation object categories for easy observation and understanding. And these two selects show result we got using the method provided by the author. And thanks for watching.
Next, I'll demonstrate the inference implementations of the GaussianFormer. Before running the model, you need to install the NVIDIA driver and CUDA Toolkit 11.8 and prepare the new things dataset. First, follow the instruction of the README to set up the Conda virtual environment and install the necessary package. The installations of this package using NVCC to compile, so it is essential to ensure that the CUDA Toolkit is properly installed. During the inference process, the GPU will be utilized, so you need to configure the GPU device ID, the model configurations file, the model weight file, the output directory, and the number of samples to generate.
And after starting the inference, you'll see the output file generated in the designating folder on the right, including voxel prediction result, voxel ground truth, and the 3D Gaussian fields using for intermediate representations by the model. And the following demonstration shows a comparison of ground truth and prediction result for two examples. That's our presentation. Thank you all.